Okay, so the recording is on now. So, good morning to all of you. So, welcome you all to take part in the fifth Gauge Gravity talk of the season two. This is an online seminar series focusing broadly on diverse topics in gauge and gravity theories. These seminars are held roughly once a month, preferably on Wednesdays. And these talks are be recorded and uploaded in the CHAP YouTube channel. So there's some instruction for the audience. So audience will be muted during the talk, and members who wish to ask questions, they can raise the hands. And if there are any urgent question, they can just post it in the chat box. And the moderator will communicate them to the speaker. So today's speaker is Professor Zhenbin Yang from Tsinghua University. He did his PhD from USTC Hefei, and thereafter he went to Princeton University to do his PhD under Professor Maldacena, and followed by which he joined as a 5-year postdoc in Stanford University. So today, Zhenbin will give comments on the DeSitter double cone. So Zhenbin, over to you.
Okay. First of all, thanks for the invitation. I'm very happy to be here to share my recent work. And I may, because of the internet connection, I may close my video because I couldn't hear the introduction very well. So I hope by closing video, you can hear me
Yeah,
better.
that is fine. That is fine.
Okay. So what I'm going to talk about is based on this recent work published in May with two students, Yuzhen Zhang and Wenwen Zheng. The topic is about some wormhole effects in DeSitter space. So let's start with a thought experiment where we think of in a d-dimensional DeSitter space, in an eternal d-dimensional DeSitter space, we have a perfect clock that runs for a time duration t with current t. If the clock has been perfect, that means the state of the clock at different times should be orthogonal. Namely, the return amplitude of the system should be 0 if t was non-zero. In this work, we ask whether this ideal clock is allowed in DeSitter quantum gravity. More precisely, we want to ask whether the system will, the state at different time will remain being orthogonal if we imagine the clock runs exponentially time in DeSitter space. So let's consider what's the effect of a clock living in DeSitter space versus living flat space. If we have a clock observer who lives in DeSitter space, then it will move around a time like geodesic, and due to the geometry of the DeSitter space, such an observer will see a static patch of DeSitter space. Namely, it will be surrounded by a horizon whose area is given by the area of DeSitter. Then, due to the Hawking radiation, such an observer will find that the DeSitter will carry finite temperature mediated through the Hawking radiation, which implies that the DeSitter horizon carry entropy, given by the Beachenstein-Hawking entropy formula. Such an intuitive idea has been made more rigorous in 2022, where Shenker, Log, and Pennington-Witten showed that using the tool of von Neumann algebra, that in the limit of G Newton go to 0, the algebra of a static patch observer in DeSitter space is type 2-1. Given a type 2-1 von Neumann algebra, one can define a von Neumann entropy, which CFTW demonstrated that the entropy of the associated von Neumann algebra is given by the general entropy of the static patch. Here, so A over 4G is a classical Beachenstein-Hawking piece, and the S matter is the matter entropy in the static patch. In particular, the algebra being type 2-1 means vacuum DeSitter will have infinite temperature. And last year, last December, when Madasina demonstrated using another method, the gravitational particle, that if you consider the severe partitioning function in DeSitter space, then due to the inclusion of observer, the severe partitioning function can be interpreted similarly as counting the total number of Hilbert space dimension of a static patch holography up to a minus sign. Here, the putable Hilbert space is given by the union of the observer Hilbert space and the DeSitter Hilbert space subject to the Hamiltonian constraint because the total system is closed. And that means that static energy of the DeSitter Hilbert space and observer had to add up to be zero. And this curly H is the actual conjecture to be the actual Hilbert space of a static patch DeSitter. And when argue that the Euclidean severe partition function can be interpreted as evaluating the total dimension of the Hilbert of this fundamental Hilbert space. So if you go and perform the severe partition function, you're first given by the classical Einstein action, and that times the observer partition function. If you carry out this analysis, you find the full partition function is minus I times a real number, a real positive number.
Zhenbin, I have a question.
Yeah.
So in the previous slide, when you showed that the partition function, this 1.5, so this decomposes into like two disjoint these pieces. So I think it is largely this is because the Hilbert space is like disjoint. Is it?
You're asking the middle line why it's a z DeSitter times z observer?
No, that I'm 1.4 I'm okay with. Now from 1.4 to 1.5. So this thing when we write the partition function as a product of these z ds beta and z observer beta. So this
Yeah.
always true, or like there is yeah, something is maybe it is always true probably.
This is true in the limit of G Newton go to zero. So
Okay, I see.
you have a classical piece times the one root partition function on the
Okay,
classical level.
okay, I see. Yeah, thank you.
Right. So this fact of I can be understood as a here there's a beta integral which effectively implement the Hamiltonian constraint, and due to the measure used the integration contour between the Euclidean partition function and the inverse Laplace transformation, that will have an additional factor of I coming relating the severe partition function with the counting of states. However, this minus sign remains unexplained. And it's still current open question how to understand this minus sign in the severe partition function. But here we assume this minus sign do not invalidate the state counting interpretation. With that being said, in this work, we want to examine the effect of the constraint on the clock system, going back to our initial question about whether there could be an eternal clock in DeSitter space. So in particular, we want to calculate the return amplitude of the system, where curly E is the clock energy, and the return probability. The letters we learned in recent years about simple model, semi-classical gravity, is that sometimes semi-classical gravity is due to ensemble theory. So these two quantities do not necessarily to be a square of each other. The return probability do not necessarily to be absolute square of the return amplitude due to some wormhole crashes. And in fact, the main take-home message of our paper is to argue that in static patch DeSitter holography, there exists a wormhole saddle that gives you non-trivial contribution to the return probability, which is non-zero at mid time. Okay, so how are we going to calculate these two quantities? We will use the tool of gravitational path integral. Here, for example, to calculate the return amplitude, uh, we will want to sum over all classical geometries that contains an observer whose clock runs from 0 to t. So it's some constraint path integral where we're only constraining the existence of a single observer whose proper time runs of time over t. And that we define as the return amplitude. And similarly, the return probability will be sum over a closed manifold that contain two observers whose clock runs from 0 to t and 0 to minus t. Okay, so we're going to explicitly discuss how to calculate this two quantities. But before we move on, let's maybe first pause and ask whether there's any questions.
Zhenbin, there is a question in the chat box.
Yeah.
So Subhashish is asking this. Maybe you can take a look at the chat box.
Okay. I have a doubt. The format and DeSitter enforcer have each DeSitter. Now, the diffeomorphism will involve the total energy to be 0. Yeah. Okay. Does that answer the question?
Subhashish, does that answer your question? Okay. He's put it in the chat box. Okay.
Okay. So let's introduce our observer model, which we use to so basically the theory will consist of the usual Einstein-Hilbert action with positive cosmological constant plus this action which describes a relativity particle that carry a clock that measures the proper time of this observer. So the observer action can consist of two pieces. The left piece is just the usual relativity particle action, where ds is the proper time of the particle. And this curly T and curly E represents the clock dynamics, where curly T is the clock time and curly E is the clock energy. You can see that if we're integrating over the energy of the clock, that enforces a debt function that the clock variable t is counting the proper time of the particle. And moreover, that's related to the question asked in the chat box. Since the whole system is living in a closed universe, we, in addition, have to portion out the gauge constraint from the DeSitter isometries when the classical background is a pure DeSitter space. So let's temporarily disregard the gauge symmetry and consider just simply this observer model of a relativity particle carrier clock. We can first consider the Euclidean propagator of the observer that is summing from passes goes from x comma 0 to x comma t. The pathing tool were given by sum over all passes of interval which described by a map from an interval to a Euclidean DeSitter space, which is SD, that parameterize the particle's trajectory with the x of lambda. And moreover, this clock path will constrain to be a monotonic map from an interval to interval. Then we have the reparametrization symmetry, which simply corresponds to reparameterize the clock trajectory. We can in order to quantize this system, we can first do a gauge fixing to fix the permutation symmetry by fixing the proper path T of lambda to be grow linear in lambda. Then this will fully fix the permutation symmetry. Then if we're integrating over the energy, then that enforces the total proper time of this propagator has to be equal to curly t, the time passes by the clock. And that reduces the path integral into sum over random passes with fixed total proper length. If we recall our first course in finite path integral, the sum of such random paths, basically it's a random walk, is described a Brownian motion in d-dimensional sphere, and that in the continuous limit, that path integral just reduced into a non-relativity particle moving in SD. With the action will be given by this standard non-relativist particle action, which describe a map from an interval to SD, which without any diffeomorphism signature. That's the difference between a relativist particle and a non-relativist particle. And this is an analog to the hydrodynamic approach of black hole thermodynamics, where, if you recall the old discussion, we have a ADS boundary, the CFT, we have, that in the IR limit will be described by some hydrodynamic action, which is describe a map from boundary manifold into a ADS Bach manifold. Here, this boundary is the interval, that's the word line of the observer, and the box space, the fluid space is SD, or it's another continuation, DSD. So yeah, let me recap. So the upshot of this discussion is that we start with an observer model, which consists of a relativity particle that describes the location of the observer in the spacetime plus a clock. And the union of these two systems gives you a non-relativity particle who's described by a word line mapped into the target space of DSD. Now, now we want to impose a gauge constraint, which is by pushing out the DeSitter isometry. Here, this DeSitter isometry is a non-compact gauge group SOD, 1. Since the DeSitter isometry is non-compact, so gauging G requires some mathematical framework called the co-invariant Hilbert space. To define a co-invariant Hilbert space, you need to do two steps. First, you need to define the vector space, and then you need to define the inner product. So in general, if you're given a pre-Hilbert space, it's H0, to define this gauging co-invariant Hilbert space, you first define an equivalence relation where the vectors in the co-invariant Hilbert space is given by the equivalence class in H0, where states are related by the action of the gauge group G. And second, you need to define the inner product in the co-invariant Hilbert space. Here, this inner product will be given by the inner product in the pre-Hilbert space and average over the action of G with a group average. And you can see that when you modify this inner product will be independent of the element in the equivalence class. And moreover, it will give you a finite inner product for a broader class of states that is gauge gauge co-invariant rather than gauge invariant.
Zhenbin,
Yeah,
what is this R of G?
R is a representation of G.
I see. Okay, okay.
So let's implement this co-invariant Hilbert space in this observer model in DeSitter space. Here in the and for now we will discuss the orienting DeSitter space. So in order to satisfy the gauge constraint, such as for example the boost energy to be zero, we need to introduce the Hilbert space will be non-trivial if we have a two observer, left and right, and this two observer will form a representation of the DeSitter isometry group. So to implement the co-invariant Hilbert space, we can first gauge fix the left observer at the north pole of the spatial sphere as d-1. So that's showing this location. Now, this gauge fixing will have a residual SOD-1, isometry, which generates this multiple orbits. And we can use the residual SOD-1, isometry to fix the right observer. So for example, if the right observer was have a location in this upper triangle, then you can use the SOD-1 to move the right observer at the south pole of the SD-1 of the spatial sphere. And after you do that, you find the gauge co-invariant Hilbert space will be given by the two particles that is antipodally located and differ by a relative time shift t. And that relative time shift is the only degree of freedom in the system, in the co-invariant Hilbert space. So the co-invariant Hilbert space is the L2 of R. And we'll, if you further do gauging the refraction symmetry, time refraction symmetry, that reduces it to L2 of R plus, where t runs from 0 to infinity. And you can work out the Hamiltonian acting on this wave functions L2 of R plus. And what you find is that this Hamiltonian takes this following form. And since there was no particles at t equal to 0, we impose a boundary condition where psi is smooth at t equal to 0. And the inner product of the co-invariant Hilbert space is given by 2.11 for d-dimensional DeSitter space. So this system requires simple solutions of its eigen system. So if you put it in mathematical to solve the to solve the differential equation 2.10, you'll find that the spectrum of the energy is given by grows quadratically in terms of some continuous variable s. So it's have a continuous spectrum and whose eigenvector is given by the hypergeometric function. And you can check out that this eigenvector satisfy the orthogonal relations and with the punctual measure given by some product of gamma function. So that describes the quantization of the observer model we introduced in DeSitter space. Okay, now with the quantization of this the observer system, let's go back to our initial to our goal. Our goal is to calculate the return amplitude and the return probability. In particular, the return amplitude is given by a path integral over a closed manifold where the observer's clock runs from 0 to t. And here, one thing I forgot to mention that this energy of this non-relativist particle, this curly E, is nothing but the clock energy. To see that, we recall that this energy is an energy conjugate to the proper time of this word line, and we have been gauge fixed the proper time to be equal to the clock time, and that means that this energy around the word line is the same as the clock energy. So to calculate the return amplitude, we will do two steps. First, we will find a classical saddle. Here, the classical saddle will be given by the usual sphere saddle. And second, we want to constrain the observer on the sphere to have a clock that runs for to evolve for time duration t. And so the sphere patching function will have the usual classical saddle classical action given by the Einstein-Hilbert action, and then to ask the contribution from the observer part, we want to look at the return probability of the observer system under time evolution t. And to do that, we need to work out the Hartree-Hawking wave function. If we cut the sphere into two parts, the observer will be if we cut the sphere patching function into two parts, then the state at t equal to 0 slice will be given by the Hartree-Hawking state of the observer, and you can work out the Hartree-Hawking state in terms of the energy eigenbasis that is given by 2.17, and then we just need to evolve this Hartree-Hawking wave function and take an overlap with itself to calculate the return amplitude. And since clock is only constrained to moving forwards, if you calculate the overlap, you find that the patching function is given by a dead function when the mass is taken. And that tells you that at the sphere level, the clock is running good, such that the state at different time are orthogonal. And next, we want to calculate the return probability. So the leading contribution will be just given by absolute value square of this return amplitude, which is given by two sphere with two observers loop, and that one will given by a dead function again. But then there is non-trivial wormhole geometry that gives you non-zero return amplitude, return probability. That is a double cone geometry. The double cone wormhole is a universal wormhole proposed by Saad, Shenker, and Stanford that can be obtained starting with any geometry with a killing horizon. And in particular, in our DeSitter case, we can take the Pelz diagram of a static DeSitter space and take a quotient with respect to the boost killing vector. And after the quotient, you will find that the singularity at the bifurcation horizon that will require some R epsilon description to go around the singularity. So the actual double cone wormhole geometry is given by the metric is given by 3.10, and that's the saddle in the limit when epsilon goes to 0. Let's make a few comments about this wormhole geometry. First, I already mentioned it is universal for any killing horizons due to the universal near horizon window structure. Is that a question? No, if not, let's continue. And second, because of this analyticity property, The whole physical quantities derived with geometry are independent of the specific regulator action because the metric is analytic in the radial coordinate. And third is that because of this quotient, this double cone contains two close time-like geodesics at the polar and antipodes, and that serves as a connected geometry for the return probability of the system, where we can put the two observers on these two close time-like geodesics to allow the clock to evolve. If you calculate the onshore action of the double cone wormhole, you find it vanishes. And that means it's exponentially suppressed relative to the leading disconnected geometry. And then the rest to evaluate its contribution reduces to evaluating the one loop determinants, which will be given by the matter perturbation function times observer perturbation function on the double cone. And there's a comment that in Einstein theory with positive cosmological constant, there actually exists a larger family of double cone geometries can be constructed from quotienting of the Schwarzschild geometry. However, such contributions will argue decays at late time. So the leading contribution is given by the quotient of vacuum DeSitter solution. So in order to calculate the contribution of a double cone, we need to calculate both the matter perturbation function and the observer perturbation function. So the first, for the matter perturbation function, because this double cone is given by the quotient of the boost evolution operator, we can interpret the matter perturbation function as evaluating a bulk trace with respect to the boost operator. And due to the I epsilon description, it actually is a some complex boost operator with k tilde, which is consists of the usual boost operator associated with the theta horizon minus R epsilon times the Minkowski Hamiltonian that is defined locally at the horizon, such that its quotient will give you this R epsilon description. And due to this R epsilon description, this the k tilde is not a Hermitian. It's a non-Hermitian operator. And its spectrum is turns out to be given by the quasi-normal frequencies of the static patch DeSitter space. And that's just general true. So in general, the spectrum of this modified boost operator is given by the quasi-normal frequencies of any static patch regimes for example, in DeSitter space. And that tells you the matter perturbation function decays to 1 with quasi-normal frequency decay. And in particular, in our current example with usual massive particles and for example, four-dimensional Einstein gravity, you find that this matter perturbation function decays to 1 after time bigger than a Hubble timescale. And if we borrow some terminology from random metric theory, where we think of this matter perturbation function as give you some non-universal behavior of the spectral form factor of the return probability, then the time scale of this non-universal piece decays to a constant determines what's called the Thoris time. And in this case, we find that the Thoris time of the static patch DeSitter space is given by the Hubble time scale. And yeah. To see, I'm not sure whether I go too fast here, but to see the spectrum of this modified boost operator is given by the quasi-normal frequency, let's consider a simple example, which is a massive scalar field. So it will satisfy the Klein-Bottom equation in the DeSitter's in static DeSitter space, and to examine the behavior, the spectrum of K tilde, we have to examine its the boundary condition near the horizon. And because of this R epsilon description, we want the wave function to go smoothly in the radial coordinate from the left static patch to the right static patch. And the smooth brewing condition requires, when you solve the field eigenvalue equation, requires you can only have ingoing or outgoing modes. And since the deformation, the modified boost operator, the imaginary part is given by the Minkowski Hamiltonian, which is positive. And that tells you that the eigenfrequency of this modified boost operator should have a negative imaginary part, and that picks up uniquely the polynomial frequency. And you can extend this argument to for more general, say, fermatic field and other fields. So the matter patching function decays to 1. What about the observer patching function? Similarly, we can also view the observer patching function of the double cone as evaluating a Bob trace. But now recall that the observer is gauge invariant, is invariant under the isometry of the gauge of the DeSitter. The observer Hilbert space is given by the co-invariant Hilbert space. That is, the state is invariant under the action of the DeSitter isometry, in particular the boost operator. And that means that when calculating the Bob trace, that reduces the trace of identity operator. And that formally counts a Hilbert space of the observer, which is divergent. But now recall that the phase space of this observer is given by the energy and the relative time shift between the left and right observer. But on the double cone, because we take a quotient, the relative time shift is actually compactified to a range capital T, which is the periodicity of the double cone. That tells you that the actual Bob trace has been compactified, and the result is finite. And that compactification of the relative time twist gives you a linear integrals of the patching function. And that gives you a ramp in the return probability. We sometimes will also call the spectral form factor, because this also mimic what we call spectral form factor in the random matrix theory. So that's roughly what it happens for the observer patching function. And to see really, to confirm really the linear integrals, we can do something more direct. That is to direct evaluating the using path integral, using one path integral to evaluate this observer patching function on the double cone. And recall that our observer model is given by this non-relativist action. So we want to evaluate this non-relativist particle action whose target space is this double cone geometry. So to do that, we can first work out the classical saddle, which is simply a static trajectory at the center of the static patch, given by the solution 3.10. And so now we can do the one loop analysis around the classical saddle. If you expand the of the observer action around the classical saddle, you find the one function, the one action given by 3.11, where this epsilon is a fluctuation of the time coordinate and xi is a fluctuation of the transverse direction.
Zhenbin,
Yeah.
I have a question. So when you say that this saddle that you're talking about, now is it like the only saddle, or there are more saddles, or is it just one saddle which is the most dominant in the path integral that you're considering?
There's the multiple saddles.
There are
That,
multiple saddles. Okay.
yeah. So, but this one is a dominating saddle.
I see. I see. I see. Okay.
Yeah, the multiple saddle could be given by the observer trajectory that it runs multiple times.
Uh-huh. But this one gets automatically picked up in the path integral, not only because it is dominant, but also it is also relevant.
Yeah.
Okay.
Well, because it's dominant, that's why it's relevant.
I see. I see.
Yeah, I'll give comment about this other saddles later. So if you're integrating with the epsilon fluctuations, you will find this linear integrals. And if you're integrating with the xi integral, then you find some exponential decay behavior. That's not surprising because the DeSitter is expanding, so its transverse fluctuation will give you exponential decaying. Just tells you classical is observed, the particle is unlikely to come back to its initial position. And if you put together the left and right observer together, you find the double cone partition function is given by 3.12, where this capital T is a periodicity of this double cone. That's a range of the boost that we quotient. And a priori here, this time duration of the clock and it's the double cone periodicity do not has to be equal. So that's why we have to integrate over this capital T. And here we introduce this measure factor mu of t that represents the density of this double cone, and we have to determine what's the measure factor later. Yeah, actually, we're going to determine here. So how do we determine this measure mu of t? So recall that this double cone is each double cone is associated. Each double cone is given by a quotient by a element in the SOD comma 1, and but you can actually construct a family of double cone with the same periodicity by conjugate the group element, and those will give you gauge equivalent configurations because those are just different by this action of DeSitter isometry. So a more proper way to think about the double cone geometry is to think about each double cone is associated with a conjugacy class in the SOD comma 1. And then the integration measure of the conjugacy class can be induced from the half measure of the original group SOD comma 1 by the well integration formula.
This when you are writing this mu of t equal to determinant prime, so this prime is derivative or exclusion of zero mode?
The determinant prime that means evaluating the mode that the action
Negative eigenmodes
of G acting on SOD comma 1 and some, but it has some null space. And this determinant means evaluate the determinant in the complement of the null space.
Oh, I see. I see.
Yeah, for example, this adjunct acting on G itself is 0.
Okay. Okay.
It just means that you evaluate the Jacobian factor in the transverse direction.
Yes. Yes. Okay. Thanks.
Okay, and so that factor, if you plug in that factor and go into the microcosmic ensemble, you recover that the one repatriation of the observer on the double cone give you just the linear integrals. Okay. So the upshot is that if you do this for one loop analysis, you find that the return probability on the double conjunction gives you a linear in T-rep. And coming to your question about the other saddles, we can consider the observer saddle have multiple windings. That can be thought of as contribution when we have n observers in a static patch. And because such observers will have a relative motion that moving apart from each other, its contribution decays exponentially. And the second is what about the Schwarzschild DeSitter double cone that I mentioned at the beginning? For the Schwarzschild DeSitter, the full isometry group reduced from SOD, 1 to SO1, 1 cross SOD minus 1. And if you use this isometry group, then you find the Y integration formula give you the measure mu of t is equal to 1. And because of this 1% t over 2 to the 2D factor, that contributes the case exponentially. And physically, that just means if you're thinking about the black hole as an ordinary matter, that exponential decay can be thought of as a cardinal mode decay of the black hole. And furthermore, for the full group SOD, 1, there exists some other conjugated class except the one associated with the boost. And one can equally construct a double cone geometry using those other conjugated class. And that can be thought of as turning on chemical potentials of angular momentum in turning on angular velocity, in other words, of the SD. What is the microscopic origin of this linear T-rep? Recall that if we using the proposal by Juan Madacina, the full system is given by the Hilbert space tensor product of the Hilbert space of the observer with the clock after with a Hamiltonian constraint. We can thinking of the bulk calculation as evaluating the trace in this fundamental Hilbert space of the evolution operator of the clock energy. Then, due to the Hamiltonian constraint, that trace is equal to the trace with where we evolve with the DeSitter Hamiltonian. And the return probability gives you nothing but the spectral form factor of H DeSitter. And the linear unity ramp can be understood as a consequence of the spectral rigidity of H DeSitter. Let me conclude. So we argue that if we include observer in DeSitter space, the DeSitter gravity naturally yields a non-perturbative small contribution to the return probability that is given by the double cone geometry. And that result is consistent with the assumption that static patch DeSitter space have a microscopic Hamiltonian H DeSitter that satisfies the random matrix universality. Okay, thank you.
Thank you, Zhenbin, for the nice talk. So now, if there are any questions, maybe the audience can also ask. In the meantime, maybe I can ask something. So when you say that this was the sphere slicing that you mentioned, that you are computing the sphere partition function, and that can be written as basically gluing of two hemispheres. Now, in one of the slides that when you showed earlier, so there's basically the sphere partition function is basically the this one. So this, I guess, is probably the most dominant contribution. So there might be additional other slicing, but they are probably subdominant in the part in this part integral.
Sorry, could you say again? What was the question?
When you say that the sphere is basically like this gluing of two hemispheres, now there might be other possibilities of slicing the sphere.
Yeah,
So, but I guess those other possibilities of might be subdominant compared to this one. This might be the
well, you
most.
can slice it whatever you want, and yeah, the calculation will be the same.
Mm-hmm,
Uh, calculation will be the same. It just comes down to different gate choice.
mm-hmm, mm-hmm.
Yeah, so you can slice different way, the biggest hemisphere, small hemisphere. So in that way, you don't take an overlap of a state with itself, but overlap of between two different states. And then you insert this just evolution operator, that will still be that function.
Mm-hmm. Okay. Okay. And this scalar, this matter sector that you are including, like this, I don't understand very well. Like, what is was the like? So you are just adding beside the standard gravitational path integral. So you are adding a matter contribution also then.
Yeah,
Okay, and in the beginning case, like you have taken into account the scalar thing.
yeah, you can include the
Okay.
scale. Yeah,
Ah. So these results then probably will still roughly say same if you have like spinners also included also.
yeah.
Okay.
Mhm, mhm. Yeah, this is the formula of product of final modes. Yeah, it
Ah,
also.
ah, I see, I see. Okay. So let's see if there are any further questions from the audience. So as of now, I don't see anything in the chat box.
So I have a question, can I ask?
Yes, yes.
Yeah, sure. So when you, in the initial slides, you said that the Z sphere is equal to ZDS times the Z observer, right? And the saddle was coming from uh, beta naught plus some I, that thing, right?
Yeah.
Yeah.
Here?
So, and yeah, yeah, in these, yeah, in beta, I suppose that beta naught is contributing to the your ZDS partition function, or even the sphere partition function. So I just want to ask that if is the beta naught defined at the asymptotic infinity of DeSitter space? Like in the ADS case, in the Euclidean cigar, you define beta at the asymptotic infinity. So
Mhm.
is it like that? Is beta not defined like that?
No, they cannot just some arbitrary constant that you used when you define the inverse Laplace transformation. When you do inverse Laplace transformation, you want the path integration contour to be the rightmost uh, that runs parallel by imaginary axis. That's what is beta not. That's not. And but maybe I think you're asking what is the definition of beta.
Yes. How do you define
Beta,
beta? Yeah,
beta is the Euclidean uh, time measured by the observer.
that is fine.
So
I was just asking if beta naught was defined at the asymptotic infinity, but I guess it is coming
no,
from contouring. Yeah, yeah.
beta, yeah,
And
it's just
in the ZDS, for generally in an anti-de Sitter flat space, you have to define Gibbon-Hawking York or the counter terms. So do you define something in
mhm.
the ZDS case also, or you just work with the Einstein-Hilbert case?
It's a closed manifold. You don't have any boundary
Okay,
term.
okay, okay. Okay.
So any further questions from the audience? So if not, then let's thank the speaker Zhenbin again for the wonderful talk and agreeing to come and give a presentation. So Zhenbin is also the first mainland China guy to give a talk in the seminar series. So it's a warm welcome to him. And so this is yeah, we last month we couldn't do the talk for because we were hosting some we were doing some conference in the this thing, so which was a gauge gravity in-person conference that we did it for the first time last month. So we are hoping that we will continue that legacy of doing the conference probably like every year. And so hopefully in the future we'll be able to do international conference on gauge gravity. And then we'll see how things goes. And yeah. So you'll be also welcome to participate in the future in the international conference also. So thank you, Zenbin, for the nice talk and for the wonderful presentation. So I'll be then, once the recording is off, we will just upload the talk in the YouTube also. Sorry, my internet just went off this thing.
Oh, okay. I thought it's mine.
No. It's I think they are doing some upgradation. So I was just saying that we will be last month we couldn't do the talk because we were doing some conference on gauge gravity and in-person conference. So we will hope that probably in future also we will do similar conferences like every year or so, something like that, and perhaps international also. So in that case, if we are doing some conference in the international level, we will be happy to invite you also. And yeah. And
Yeah.
that's
Yeah. I
wonderful.
do appreciate it. Yeah.
And you are the first speaker from
Invitation and
the seminar series. So thank you very much.
okay. Wow. Thank you.
Yeah.
I'm very honored.
Bye bye.
Okay. All right. So, yeah, hope to see you guys in
Yes, sure.
future
So we will be
events.
putting the recording in the
Bye.
YouTube also.
Mhm.
Yeah. And then we will share the recording. Then you can also take a look at it.
Okay. Okay.
Okay.
That's
Yeah.
good.
Bye. Mm.